Okay, let's unpack this. Today's deep dive tackles a question I think many of us grapple with. What really separates the exceptional from, well, the rest of us?
Hmm.
Is it pure talent, something you're born with? Is it just sheer hard work? Or maybe something else entirely?
It's the perennial question, isn't it? Nature versus nurture, framed in achievement.
Exactly. And we've pulled together quite a stack of sources today. We've got research on athletic performance, genetics, training, drawing quite a bit from things like the sports gene.
Ah, yes. Good stuff there.
And we're pairing that with insights from, perhaps surprisingly, orthopedic knowledge updates things touching on human variability, complex decision-making assessment.
Which might seem worlds apart, sport and trauma surgery, but the underlying principles.
That's what we want to explore. Our mission really is to pull out the key nuggets on expertise and achievement using sport and medicine as these, well, fascinating case studies.
Looking for those universal threads.
Precisely. So get ready for maybe some surprising facts, perspectives that might just make you think differently about talent and performance, even in your own work.
Absolutely. It's
Yep.
fascinating how looking at elite sport, pushing physical boundaries, and complex trauma surgery, pushing cognitive and technical limits.
How they can both illuminate these core ideas about high performance.
Definitely. Both involve navigating the very edge of human capability.
And one idea that seems to have really, taken hold in popular thinking is the 10,000 hours rule. Practice makes perfect, essentially.
Ah, yes. Often linked to Anders Ericsson's work on deliberate practice, it's certainly permeated the culture.
But our sources, looking at them together, they seem to suggest it's maybe a bit more nuanced than just clocking up the hours.
Precisely. I mean, accumulated practice is undeniably crucial.
Hmm.
Erickson himself, I believe, called it the real wizard behind the curtain.
Uh-huh.
No one doubts its importance. But the way it's often interpreted in the media,
Yeah.
this idea that anyone can hit expert level with 10,000 hours and that no one gets there with less, that's a real oversimplification.
All right.
Even Erickson and his co-authors, when they started incorporating genetics, initially argued the necessary genes were common to all healthy individuals, making practice history the differentiator.
Okay.
But the sources we're looking at, taken as a whole, they really paint a richer, more complex picture.
Yeah.
They show the effect of practice isn't uniform at all.
So it's not just the quantity of practice, but maybe how our biology, our underlying makeup, interacts with that practice.
Exactly. The sports gene source really dives into this, showing how different bodies can respond so differently to the exact same training program.
How so? Give us an example.
Well, think about aerobic training. There's
Yep.
a large-scale study called Heritage that stands for Human Exercise Response to Training in Heredity and Genetics.
Oh.
They put a diverse group of people through a standardized exercise program and tracked how much their aerobic capacity improved, basically, how well their bodies got at using oxygen.
And the results.
Remarkable variability, just huge differences. You had some people, the high responders, who saw massive improvements in their fitness,
Right.
but then you had others, the low responders, who saw very little improvement, or sometimes none at all, from the exact same training dose.
Wow. So same work in, but wildly different outcomes depending on your sort of biological lottery ticket.
That's the core takeaway here. An editorial commenting on similar findings, I think it was in the Journal of Applied Physiology, put it quite bluntly. It suggested that for low responders, their predetermined genetic alphabet soup just may not spell runner.
Quite a statement.
It points very clearly to this biological variability influencing trainability itself. You can put the hours in, absolutely, but your genetic makeup seems to profoundly influence how much your body adapts and improves from that effort.
That's a really key point. It certainly challenges the simple effort equals outcome equation, doesn't it?
It does.
And beyond just how trainable we are, the sources also talk about specific physical traits becoming almost essential in certain sports, certain contexts or games, as the source calls them.
Quite right. Professional sport has, in effect, become this huge sorting mechanism. Maybe a natural selection laboratory or perhaps artificial selection is better
Sorting for what?
for specific physical attributes. Individuals with certain body types are increasingly channeled into sports where those traits give them a distinct advantage. We're seeing what the source calls extreme self-sorting,
Meaning?
meaning elite body types for different sports are diverging quite rapidly, actually. Think about elite distance runners. They're tending to get shorter over time.
Okay.
Compare that to elite volleyball players or rowers. They're getting taller, larger. The demands of the sport are selecting for these forms.
And it's not just overall size, is it? I remember reading about gymnasts
Not at all. Female gymnasts, yes, they've shrunk significantly over the last few decades. And conversely, think about track and field. Tall women are hugely overrepresented in Olympic finals compared to shorter women.
So the specific game dictates the ideal physical toolkit in a way.
Seems so. It's more than just training. It's a fundamental physical difference being amplified by the competitive environment itself.
There was another example cited about throwing, the difference between boys and girls even when young.
Yes, the throwing gap. It appears very early, and intriguingly, it seems to persist even in cultures where you might expect less differentiation. The source mentions studies in some Aboriginal Australian communities where girls were taught to throw for hunting, just like the boys.
But the gap remains.
The gap remained. Now, this isn't about saying one group is generally better, but about understanding specific, measurable biological differences.
Like what in this case?
The sources mention evidence suggesting, for instance, that boys develop a slightly longer forearm in the womb.
Really? Before any practice difference?
Potentially, yes. And that small difference could contribute to altered throwing mechanics right from the start, independent of practice or cultural nudges.
Fascinating. And then you have those famous examples, populations known for dominating certain sports, like the Kalenjin runners from Kenya or Jamaican sprinters.
Ah, yes. Those case studies are always compelling, aren't they? They force you to look beyond just individual effort. Take the Kalenjin.
Incredible dominance in distance running.
Astonishing. The source mentions that in just 1 month in 2011, 32 Kalenjin men ran a marathon faster than 2 hours, 10 minutes.
32 in 1 month.
Compare that to, I think, only 17 American men in history who have ever achieved that time. Or consider St. Patrick's High School in Kenya. It apparently had 4 sub-4-minute milers at the same time.
That kind of concentration, it's hard to explain purely by training volume, even though they obviously train incredibly hard.
It really makes you consider other factors, doesn't it? Genetic predispositions, unique environmental factors, cultural emphasis, perhaps. It's likely a complex mix.
The source mentioned the history of the Maroons in Jamaica as a possible factor for sprinting prowess.
Yes, the idea linking it back to these selection pressures during slavery and the formation of the Maroon communities. One expert called it a convenient story, perhaps too neat.
But the overall pattern across different sports, different populations?
It is striking. It points strongly towards this complex interplay of nature, nurture, environment, culture, all tangled together.
But the source was also quite conscious about the idea of finding a single athlete gene, wasn't it? That feels too simplistic.
Absolutely spot on. That was maybe an early hope when genome sequencing took off, find the gene for speed or the gene for endurance.
But it's not like that.
No. We now understand the biology is far more complex. Many, many genes contribute small effects to athletic traits. And importantly, different combinations of genes, different pathways, can actually lead to similar physical outcomes.
Okay, so no single magic bullet gene.
And crucially, even within groups that might seem predisposed, there's still massive individual variation. The source shows the example of how people respond to altitude training.
Right.
When exposed to altitude, some athletes see a big jump in their EPO levels, that's erythropoietin, the hormone stimulating red blood cell production, good for oxygen transport.
Which is what you want for endurance.
Exactly. But other athletes exposed to the same altitude, their EPO levels actually declined.
So even within potentially talented groups, there's huge biological variation in response to specific challenges like altitude.
Precisely. It's described as a complex braid, nature and nurture, genes and environment all woven together. You might have the biological potential, but you absolutely still need the right environment, the coaching, the thousands of hours of focused practice to realize it.
And the flip side?
The flip side is you can practice incredibly diligently, but your individual biological response to that practice or your fundamental physical attributes might set a different ultimate ceiling for you in a highly specialized sport compared to someone with different inherent characteristics.
It really makes you think about how we measure potential, how we predict success, not just in sports, but, well, anywhere.
Exactly. And that's where the parallels with our orthopedic trauma sources become really quite striking.
How so?
Because in trauma, you're also dealing with immense variability in patients, in injuries, in responses to treatment. And just like searching for a single athlete gene proved too simple, relying on simple metrics often falls short in complex medical situations too.
Okay. So in orthopedic trauma, the challenge is predicting outcomes, making critical decisions, often fast, with incomplete information. The sources mention trauma scoring systems.
They do. These systems, like the Injury Severity Score, ISS, or the Revised Trauma Score, RTS, were developed with good intentions, trying to objectively quantify how badly someone is hurt to guide treatment.
Makes sense.
And there are more specific ones, like the Mangled Extremity Severity Score, or MESS. That was developed back in the late 80s, early 90s, specifically to help surgeons decide whether to try and save a severely injured limb or if amputation was the better course.
Seems like a useful tool. But you said simple metrics fall short.
Well, yes, these scores provide valuable data, but relying solely on them has limitations. Research on the MESA score, for example, found its predictive value for whether limb salvage would succeed was only around 50%.
Only 50%. That's basically a coin toss.
Pretty much. And perhaps more telling, another study showed that 20% of patients who did have their limbs successfully saved had MES scores of 7 or higher, a level originally considered a strong indicator for amputation.
So the score alone wasn't the deciding factor.
Experts really caution against using MES in isolation for day-to-day decisions now. Why? Because surgical techniques, critical care, our ability to manage infection and promote healing have all advanced significantly. We can now save limbs that might have been deemed unsalvageable based on those older score thresholds.
So just like the 10,000 hours rule or the athlete gene idea is too simplistic in sport.
Exactly. Relying only on an anatomical score like MSS is insufficient in complex trauma. You need much more than just the number.
The score is data, but it needs interpretation within a broader context.
Precisely the parallel. The expert surgeon integrates that score with countless other factors. Think about injuries to the hip socket acetabular fractures.
Okay.
Surgeons have tried using specific radiographic measurements, the size of bone fragments, angles, things like that, hoping to predict if the hip will be unstable after it heals.
Yeah.
They provide some information, sure, but they've only been marginally successful as standalone predictors. Hip stability is complex. It depends on the exact fracture location, the socket's orientation, how well the ball part of the femoral head is covered, whether the hip dislocated initially.
That's of variables.
Exactly. So ultimately, the gold standard often involves examining the hip stability directly under anesthesia in the operating theater, because no single measurement tells the whole story. You need that dynamic assessment.
It sounds much less like following a formula and much more like synthesizing diverse information streams, including real-time feedback in the OR.
That's a great way to put it. And the goal isn't just fixing the bone. It's about promoting healing, restoring function long-term. This brings in more biological complexity and the nuances of surgical technique.
How so?
Well, fracture healing isn't just about lining up the pieces perfectly, though anatomical restoration is important. It's also about choosing the right fixation. The plates, screws, rods, and applying it in a way that encourages the right type of healing for that specific fracture and that specific patient's bone quality.
There are different types of healing.
Broadly, yes. And new technologies in implants, like locking screws or dynamic constructs, give surgeons more options. They can make the fixation very rigid or allow a tiny bit of controlled movement, depending on what's needed biologically at the fracture site.
But the sources mentioned these advances can sometimes have downsides too.
They can, yes. For instance, if you make the fixation too rigid with some modern locking plates, particularly in certain fracture types, it can sometimes paradoxically slow down or hinder the natural secondary bone healing process, which actually relies on a bit of micromotion to stimulate the bone-forming cells.
Ah, interesting. So it's not just about having the latest gadget.
Not at all. It's about the surgeon's deep knowledge, understanding the biology, understanding the technology's capabilities and limitations, and choosing and executing the optimal strategy for that unique biological and mechanical situation. It's highly context-dependent decision-making.
That sounds incredibly complex. Very much like an elite athlete adjusting their race plan based on how their body feels or what competitors are doing. It's expertise far beyond just rote procedure.
Absolutely. The orthopedic sources really hammer home the importance of this complex decision-making, whether it's planning for mass casualty incidents like the Boston Marathon bombing response or the Haiti earthquake, where resources are suddenly overwhelmed.
Right, extreme circumstances.
Or even in more routine, complex cases, like debating the optimal timing for fixing fractures in patients with multiple severe injuries. There are biological windows, physiological considerations. It's rarely straightforward.
Even amputation was reframed, wasn't it?
Yes, the source made a point of framing amputation not as a failure, but sometimes as a necessary reconstructive procedure. The goal is to create the best possible residual limb to allow for optimal function with a modern prosthesis. It's about maximizing future potential.
And recent advances seem to be leaning more into understanding the biology, not just the mechanics.
Precisely. Things like targeted muscle reinnervation, TMR, or targeted nerve implantation, TNI. These are fascinating surgical techniques used during or after amputation.
What do they do?
Essentially, they involve rerouting the severed nerves from the amputated part into nearby remaining muscles. This gives the nerves a new job, a functional purpose.
And the benefit.
It can significantly reduce phantom limb pain, which can be debilitating. And excitingly, it can also provide clearer signals for controlling advanced, mind-controlled prosthetic limbs.
Wow, that's really blending biology and technology.
It is. It stems from understanding the nervous system's biological response to injury and finding clever ways to harness that response for better function. Again, it's biological insight combined with technical surgical skill.
It really does highlight that interplay between the patient's complex biology and the expert's intervention and decision-making. It's definitely not just a mechanical fix.
No, it's deeply systems-based. The sources on polytrauma patients with multiple severe injuries stress the need for multidisciplinary teamwork. It's driven by trauma surgery, yes, but needs constant integrated input from neurosurgery, radiology, emergency medicine, anesthesia, critical care,
A whole team synthesizing information.
and using biological markers to guide decisions. For example, tracking venous lactate levels, basically a measure of oxygen debt in the tissues, helps gauge the patient's overall physiological state and whether they're stable enough for major definitive surgery, a biological reading informing a critical technical decision.
It really is a systems approach, isn't it? Whether it's the athlete's body performing at its limit or the trauma patient's body responding to severe injury, they're both incredibly complex systems. And the outcome depends on so many interacting factors, way beyond simple inputs like hours practiced or fixation method or a single score.
Precisely. It boils down to understanding inherent human variability, assessing performance or injury across multiple dimensions, and applying deep expert knowledge to navigate complex, often unpredictable situations.
So metrics, tools, training data, genetic profiles, trauma scores, they're valuable.
Incredibly valuable, yes.
Yeah.
But they are aids to complex decision-making, not replacements for it. Expert judgment integrates all these data points with a fundamental understanding of the underlying biology and mechanics.
That feels like a really fundamental truth, actually, something that cuts across high achievement in almost any complex field.
I think so.
Whether you're an athlete, a surgeon, a leader, whatever, focusing just on one thing effort alone, or supposed innate talent, or hitting one particular metric, it just fails to capture the whole story of what leads to truly extraordinary results.
So what does this all mean? Well, this deep dive into our sources today, looking at everything from athletic genetics and training science to the complexities of medical assessment and outcomes, it really reveals a crucial insight, I think.
Which is?
That what makes someone truly extraordinary is rarely, if ever, down to just one single factor.
Right. We've seen that dedicated practice is vital, absolutely essential.
But the response to that practice varies enormously, influenced by our individual genetic and biological makeup.
And the environment or the game itself shapes which traits become advantageous, like a specialized body types in sports, or how different people respond physiologically to altitude.
Crucially, simplistic ideas like hunting for a single athlete gene, or relying only on the 10,000 hours rule, or using just one anatomical score in trauma, they just fail to capture the full, complex picture.
So extraordinary performance emerges from this intricate interplay of nature, nurture, and context.
Exactly. So as you reflect on talent, training, performance, maybe in your own professional life, perhaps the provocative thought to leave you with is this.
Go on.
How can you move beyond relying on simple metrics or single explanations? How can you embrace this more nuanced, complex understanding to really unlock potential both in yourself and in others you might lead or mentor?
That's a great question to ponder.
It challenges us to look deeper.
Indeed. And if you found this deep dive valuable today, please do consider taking a moment to rate and share the show. It really helps others find it.